Welcome to General Structures 2 Lateral Forces, Lesson 4, Earthquake Design Example, Part 3. And where I left off, and I kind of rushed a little bit at the end, so I will back up and explain in depth what we're doing here. If you remember, we're looking at the diaphragm, which, let me switch colors here, is, actually it's down right here, but we're saying, for simplicity, it's the roof. It's down there because we have parapets, but so we're looking at the roof diaphragm, and we're wondering what's the max. Oh, let me go back and explain. First of all, what was the max shear at this point? So you're going to be putting a diaphragm down right here. That's your diaphragm. So we need to figure out what was the max shear. As you know, when you look at a shear and moment diagram, so this is your shear diagram. Your shear diagram for a uniformly distributed load will look something like this, where in the middle, sorry, this is not perfect, it's 0, and at the ends, it's your max. And we did this in the last video. We found out what our max is, so right here and right here, and that was that 40,650. And then we divided by that 60 foot to figure out what type of diaphragm we needed. So the plywood, what kind of plywood we needed. Now they asked us to calculate the maximum chord force in the diaphragm. So that was the shear force. Now we're looking for the chord force. And as I tried to explain last time, maybe I'll try to change colors again. See if you can see this blue. Yeah, I guess you can see it. Is you're going to have tension in the top chord, or let's say the bottom chord, and compression in the top chord. And that's assuming, once again, that the loading is going this way. And that's the assumption. If it goes the other way, which it can do, so not that it matters, but either way, we need to figure out what that chord force is. So that's what we were doing. Let me go ahead and erase some of this stuff right here. And we'll go back to how do you find that chord force. And to get that chord force, what you want to look at is it's similar to a truss, where if you have a top chord, you have a bottom chord, and then you're going to have your, so you don't have to say it's a truss. It could be just a beam, but I like to look at it as a truss, because let's say you have a truss where that top and bottom chord, if you look at it anywhere, or especially if you look at it, if you cut it as at the joint, then you need to have this, you're going to have a force right here, and you're going to have a force right here. You're going to have compression force on the top and a tension force on the bottom, and then you're going to have this moment arm right here between the 2 points. You can call that D, I guess. And that's going to be your moment. It's going to be, if you sum the forces about this point, so it's going to be this force times this distance, this force right here times this distance, you'll get your moment. So that's what we're looking for to do right here. We want to figure out what our moment is, and you can find your moment based on the WL squared over 8, since it is a uniformly distributed load. And then you can divide it by this D, which is going to be, in our case, 60 foot, because remember this is our D right here. So let's go ahead and figure that out, and you're going to get the compression or tension force. And the reason I said multiply by this distance times that force, these forces will be equal, and it depends if you, let's call this A and this B. So if you sum the moments about this point, it's this force times this distance. If you sum forces about A, it's this force times the same distance, and therefore they're going to be equal, and it does not matter which way you do it. Or you could sum the forces about point C, assuming it's right in the middle, or it could be anywhere along there. Excuse me. And it would be this force times d over 2 plus this force times d over 2, which is going to be the same. So if you didn't understand what I just said, don't worry about it. Let's move on. And we have WL squared over 8 to get the moment, the max moment, and that's going to be at the center line of this beam, or the center line of this diaphragm, which is going to be at 175 foot. So anyways, we want to say W is, once again, it's at 542. And it's easy to go ahead and just draw this. Remember, we're looking at it as a simple beam with a 542 pound distributed load on it. That's looking in the XY plane once again. 542 PLF. And that's 183 plus 183, and those are both from each wall, plus the roof is 176 pounds per linear foot. Alright, so we have PLF. We're multiplying that by 150 foot. That's going to be squared, and then we'll divide that by 8. So 542 times 150 squared divided by 8. And you get, our moment's going to be, I should probably say moment, not to confuse you, is 1,524,375 foot pounds. And I would say it's 24.4. Whoa. That's 24.1 foot kips. So as you can see, you can get rather large when you get in the foot pounds. So that is where we are at. And then we want to divide that by our D, which is 60 foot, which you could say is the depth of the beam, or the depth of the truss. In this case, it's the depth of our diaphragm. So let's go up here, 1,524.4 foot kips divided by 60 feet. And you could say that this is M divided by D equals your, which might be confusing, so I would just think of it intuitively. Think of it as a truss. This is our diaphragm. So if you're looking at our truss per se, where instead of these diagonals, it's the diaphragm is our diagonals. And this is the plan view. Not plan. Yeah, plan. That's what I'm talking about. This is the 60 foot. This is the 150 foot. Maybe that is better since I drew that isometric view. And you can see that when we do that, then we put the 542 going that way, and then we flipped it up, and that's where you're looking at it. So hopefully that all makes sense. If it doesn't, just send some comments, and I can come back and maybe do a video response and help out. Anyways, back to where we were, without getting too sidetracked. I'm going to divide my current answer by 60, and I get 25.4 kips, or was that 25,406 pounds. So 25.4 kips is fine. And that is our, once again, that was what we were trying to find for our maximum chord force. And just to reassert the fact that it can go in either direction, I'm putting it in this, all the forces in this direction to begin with. But remember, in an earthquake, the bottom will move. It'll create that force in one way, and then it brings it back the other way. So you'll see this relatively the same force, obviously. Just like any, if you take something and flick it, a ruler, it gets shorter and shorter every single time the period does. So, or at least the distance that it deflects. If you look at it, it'll be like this. If you look at your ruler, and then next it'll be like that and like this, and it'll slowly get smaller and smaller, kind of like a spring. But so that initial, whichever way it pulls first, will be initially the larger of the two, then it'll slowly get smaller, smaller, smaller. But that is our chord force, 25,406 pounds. And you can resist this force by a few different ways, but it does, you need to take into account, it does need to be resisted in this wall and in the roof diaphragm. Alright, I hope that helped, and I will see you on the next example.